Okay, we continue to prove the following theorem. For a matrix A, the pivot columns of A form a basis for its column space. All right, so we consider A, for example. Suppose that the matrix A has 6 columns. Right, and it's reduced the echelon form. Okay. So this is the reduced echelon form of A. And we know this is pivot. All right, so we have a pivot in the second columns, so that the second columns, the fourth columns, and the sixth column, they are called pivot columns. Okay, they are pivot columns because that A has a pivot position in the second column, so this is the 1-2 position. It's a pivot position in A, and 2-4 is a pivot position in A, and 3-6 is a pivot position in A. So the corresponding column A2, A4, and A6 are pivot columns of A. Questions? Okay, so now our purpose is to show that these 3 columns, A2, A4, and A6, form a basis for the column space of A. All right, so now look at, so they are pivot columns of U. Okay, and the pivot columns of U they are E1, E2, and E3. Okay, and the pivot columns, by the definition of a reduced echelon form. For example, the first pivot column should be 1, 0, 0, 0. Must be this one. And the second pivot column from the left should be 0, 1, 0, 0, 0. And the third pivot column in U should be 0, 0, 1, 0. Okay, so that would be okay, and the rank up to ER is the rank of A. The rank of A is the number of pivots, right? The number of pivots A has. Okay, so that in here, the rank of A is 3, so it has 3 pivots, and it has 3 pivot columns, and these 3 pivot columns will be E1, E2, E3, E4. Okay, maybe I will later. Right, so we have that pivot columns of U are E1, E2 up to ER, with R is the rank of A. Okay? So we know the pivot columns are the standard unit vectors. Okay? So they are okay? So the pivot columns of A are standard unit columns. And form a linearly independent set, of course, right? Okay, so pivot columns of U, right, are this standard, and they form a linearly independent set. And also each non-pivot column of U, okay, each non-pivot column of U is a linear combination a linear combination of pivot columns of U. Okay, so when we look at the U, you see pivot columns of U are standard unit vectors. So are standard. Okay, so pivot columns are standard unit vectors, E1, E2 up to ER, with R to be the rank of A, and form a linearly independent set. And secondly, each non-pivot columns is a linear combination of the pivot columns U. So you see that, of course, the all zero column just is trivial to be a linear combination of pivot columns of U. Just put in the zero coefficients. And for this one, this is a non-zero, non-pivot column. So because this one can be spanned by 1, by this, okay? Because you have, if an arbitrary entry is only here. And for these pivot columns, you have only 2 arbitrary entries here, can be spanned by this pivot column and this pivot columns. Because of the echelon form, right? This is because that okay, because of the echelon form. So non-pivot columns of U is a linear combination of pivot columns of U. Obviously, right? This is the specific definition of an echelon form, reduced echelon form there. Okay, now, so this is our observation about reduced echelon form. It's quite easy because the reduced echelon form is very simple. Okay. Now, all the linear dependency of columns in U will have a corresponding linear relations on the columns of A. Why? Okay, now, so this is the bridge. Now, a linear relation, right? A linear relation on the columns of A. Okay, for example, you have x1, A1 plus X2, A2 plus plus Xn, An equal to the 0. So this is a linear relation, right? On the columns of A. And this one can be written by a matrix equation. Okay, so this is equal to A, X equal to 0. Okay, so a linear relation corresponding to a solution of this homogeneous linear system. And so this corresponds to a linear relation on the column of U. Okay, so we have x1, u1 plus x2, u2 plus xn, un equal to 0, which is u1, u2, un equal to 0, corresponding to u equal to 0. Why? Why a solution, a linear relation on columns of A has basically the same linear relation because the coefficients are the same on the columns of U. The reason is that the kernel of A is equal to the kernel of U. Because A and U are row equivalent to each other, right? So when you have two matrices which are row equivalent to each other, then they will have the same kernel, right? And we prove that by theorem in chapter 1, 1.3.5. Okay? So they will have the same, because A and U and they are row equivalents, okay, so they will have the same solution space. Okay. This is the reason why we do the Gaussian elimination, right? So that because they have the same solution space, so a solution X here will be a solution in here, so that if we have a linear relation for columns of A, we have the exact same linear relation, okay, because for the columns of U. All right, so this is one-to-one correspondence. All right, and now we have the data here. First of all, the pivot column of U form a linear independent set. Okay, so from this data, so we have this one and this one, right? We get to here. That pivot columns of A, right, form a linearly independent set. So immediately we know the pivot columns of A, right? The pivot columns of A form a linearly independent set. Because pivot columns of U, right, form a linearly independent set. Secondly, each non-pivot column of A, all right, is a linear combination. Actually, the same linear combination, all right, of pivot columns of A. So immediately we have this one. So they are correspondence here of them. Questions? Any questions? Okay, so now pivot columns of A form a linear independent state, and each non-pivot column of A is a linear combination of pivot columns of A. So now the column space of A is the span of A1, A2 up to AN, okay? And then now, in this set, if we have a column, because in here, each pivot column is a linear combination of pivot columns. I'm sorry. Each non-pivot column is a linear combination of pivot columns. So they can be removed, right? So they can be removed from the list here. So that equal to the pivot columns of A by removing non-pivot column one by one by theorem of 5.2.8. Removing of, so we can move one column one by one. Okay, and then without changing its span. Okay, so that is the idea of theorem 5.2.8. Okay, so in this example, because A1 is a linear combination of A2, A4, and A6, so A can be removed first. And the span of A1, A2, A3, A4, A5, A6 is the same as the span of A2, A3, A4, A5, A6. Next, because A3 is a linear combination of A2, A4, A6, so A3 can be removed again without changing its spanning set. And the last one is to remove A4, A5. So A3, A1, A3, and A5 can be removed without changing the spanning set. Okay, so that is exactly here said. Okay, so that the column space of A is spanned by the set of pivot columns of A. Right, so with this one here and this one here, so the set of pivot columns is a basis for the column space of A. Okay, so this is the end of the proof. Questions? Questions? Okay, so now a remark. So the dimension of the column space of A is equal to the size of columns of A and this is equal to the rank of A. Okay? So the dimension of the concept of A is equal to the rank of A, and the dimension of the concept of A is called the column rank. Okay, so people call this called the column rank of A. Questions? All right. So if no questions, then I move on to the next theorem. Suppose T from V to W, a linear transformation. So if T is here, then the dimension, okay, and this one is finite dimensional. And but W can be arbitrary, can be finite dimensional or not finite dimensional. But the domain V is finite dimensional here. Okay, then the dimension of the range of T is less than or equal to the dimension of V. Okay. So in this course, we define dimension of V when V is finite dimensional. Okay, because if V is infinite dimensional, then its dimension can be defined, but you need some transcendental number theorem. Okay, and so that is well, we need some elaborations. It's not necessary in this course, so I just ignore it, right? So we just consider, we define dimension only for finite dimensional vector space. All right, so if T is a linear transformation from a finite dimensional vector space to a general vector space W, then the dimension, then we will see that the range is also finite dimensional. That's why we have dimension, okay? So the range is finite dimensional, and its dimension is less than or equal to dimension of V. Okay. So now the proof. So let n equal to the dimension of the V here. Okay. And B, V1, V2 up to Vn, a basis for V. Okay, so suppose we have this setting up. Then we have, so we look at the range of T, so that the range actually is defined to be the set of all images of vectors in the domain V here. Okay, but because B is the basis of the vector space V, so every V can be written as a unique linear combination of the basis vectors scalars. Okay, so we can write down immediately that this is the range here. And the bilinearity, this is actually alpha 1 t v1 plus alpha 2 t v2 plus alpha n t vn given alpha 1, alpha 2 up to alpha n scalars. Okay, so this is actually the span of the images of basis vectors. Okay, so the image is spanned by a set of size n. Okay, so that's by theorem we just developed before, by theorem 5.2.11, that if a vector space is spanned by a set of n vectors, then the vector space is finite dimension, and its dimension is less than or equal to the size of the set. All right, and which is equal to n, and this is the dimension of V. Okay, and we have done. Okay, so you can regard it as, but this as an index set, all right? But if you regard it as just a set, then that the size of this set will be less than or equal to n, because some of this image are the same. But even this is true. You regard this as a set of vectors, not index set, even though you regard it as a set only. Then you should have less than or equal to n here. And again, you have the same inequality. So that's a major. How you regard this set as index or non-index set. Now, okay? Okay, so next theorem. Any linearly independent set X in a finite dimensional vector space okay. So if we have a linearly independent set in a finite dimensional vector space V, then this linear can be extended to a basis for V. Okay. Well, this has been proved already. I think in chapter 2. Okay, but in the context of chapter 5, we may give a proof, right? Okay, so suppose that the dimension of V is n, and the size of the linearly independent set is k. Okay, so now, of course, by theorem 5.2.12, 12, we know that k should be less than or equal to n. Okay, because that if a vector space has a linearly independent set of size k, then either this vector space is not finite dimensional, or its dimension is at least k. Okay, so that is the theorem 5.2.12. Okay, so we have this inequality. Okay, immediately by the theorem here. All right, so now if k equal to n, then x is the basis. Why? Okay, because this is theorem 5.2.10. Okay, so if we have a linearly independent set of size n in an n-dimensional vector space, then this linear independent set must be a basis. Okay, so if the size of x is equal to the dimension of v, then x is a basis already. So we have done. You don't need to do any extension. It's already there, right? So extension is not necessary. But if k is less than n, okay, then the span of x must be contained in V but not equal to V. Alright. Otherwise, if if x is span V, otherwise the dimension of V, because x is a spanning set, so that would be less than or equal to k, the size. If the spanning set, will be equal to the. Otherwise, if x, so otherwise x is a basis for V. Why? Because x is already a linearly independent set, and if this is true, if the span of x equal to V, and then x is the basis of V, and then okay, so this is a contradiction. It's impossible because we say k is less than n. All right. So now, we have v here. We have the span of s here. So now we can select vk plus 1 out of the spanning set here. So we have a situation. All right, so we pick up a vector vk plus 1 in V but minus the span of x. Right? So we pick up then x union vk plus 1 is a linearly independent set again. By theorem 2.4.11. Okay, so now for the extension, so we can now if k plus 1 equal to n, then x union vk plus 1 is a basis for V, and we have done. Okay, if k plus 1 is still less than n, so we continue extending, we continue extending the resulted linearly independent set by adding vectors one by one until a linearly independent set X union Vk plus 1 up to Vn is obtained with the size of this union is equal to n. Okay, so then this union is a basis for V. Okay, and then we finished the proof. So this is basically the procedure we discussed before in chapter 2 in Theorem 2.4.11. Okay, so every time if the span is not the full vector space, then you can pick up a vector outside of the span and enlarge the linearly independent set. Okay, enlarge by 1. And then you will stop. Why? Because the vector space is finite dimensional. Okay, so this process cannot be done indefinitely, right? It should stop. So that is the idea. Questions? Okay. Now, next theorem is one of the main theorems in this chapter. So T is V equals to W, a linear transformation, Okay, and here again V is finite dimensional, and the W can be arbitrary, may not be finite dimensional, or may be finite dimensional, but we just require the domain V to be finite dimensional. Okay, so we need that. All right, so if we have such a linear transformation T, then we have the result. The dimension of the kernel of the linear transform T plus the dimension of the range of T is equal to the dimension of the domain V. Okay? So we have a conservation law, right? We know for a linear transformation, there are two important subspaces. One is kernel of T. Kernel of T is a subspace of the domain. The range of T is a subspace of the codomain. Okay? So these two subspaces are important subspaces associated with a linear transformation. But their dimensions has a conservation law. Means that the sum of the dimension of the kernel and the dimension of the range is equal to the dimension of the domain. Okay. All right. Right, we just proved theorem 5.2.14 that TV, the range is finite dimensional. And its dimension we call M is less than equal to the dimension of V. Okay? So we know from the theorem 5.2.14 we get this result. Right? Also, since the kernel of T is a subspace of the domain, a basis called C a basis for kernel of T is a linearly independent set in the original vector space V, and then we define K to be the dimension of kernel of T. This is equal to the size of C. So the size of C, because C is a linearly independent set in V, all right, so that this is less than the dimension of V again. Okay, so now at the beginning we know the dimension of the range of T, which is called M, is less than equal to the dimension of V, and also the dimension of the kernel of T is also upper bounded by the dimension of V. Okay, so we have these two facts. Okay. All right, and so to prove the conservation law here, now we use the following setup. Right, let U1, U2 up to UK, right, be a basis for the kernel of T. Okay, because there the dimension of kernel of T is assumed to be K. Okay, and let W1, W2 up to Wm be a basis for the range of T. Okay, so we have that. Now, for each Wj, there exists a V J such that Wj is equal to T Vj. Okay? Because Wj is in the range of V. So each Wj, okay, we can find a vector in the domain such that Wj is the image of the vector Vj. Okay? So we have that. Okay, and we will show that we will claim the set defined by U1 up to UK, V1 up to Vm. So we collect them, U1, U2 up to UK. They are a basis in kernel of T. And of course, they are vectors in V, right? And also, V1, V2 are vectors in V. So that we collect them together, we will claim that this is a basis for V. Okay? So we'll claim this is basis for V. All right, to show it, we have two parts to prove. One is to show that the set span V, right? So V, every vector in V is in the span of this set. All right, so we let a vector in V. All right, then, of course, the image of V is in the range, right? So that, and then TV is equal to alpha. Maybe I use beta. So beta 1, W1 plus beta 2, W2 plus beta M, Wm. Why? Because this is a basis for the range. So that every vector in the range is a linear combination of the m basis vectors. Okay. All right, and this is beta 1, Bv1, Tv2, beta m, Tvm. But Wj's are image of Vj's. And so by linearity, okay, right? So now, so the image of V is equal to the image of a linear combination of V1 up to Vm. So this says that V minus beta 1, V1 plus beta m, Vm is the zero vector. So that this implies that the difference is in the kernel of T. Okay, so it's in the kernel of T, and in the kernel of T, so that this vector can be is in the kernel of T, right? So can be spanned by UIs. Okay. And finally, V itself can be written as a linear combination of UIs and Vj's. So this is implies that V is in the span of the B set, because B is in there. Okay, so V is contained in the span of the B set. But the span of B is also a subspace of V, of course, so that V is equal to the span of B. Right? So this is the first part. So now B is the span of B. Okay? All right, so now we have to prove B is a linearly independent set. Right. Now, consider a linear relation on B. Okay? So the linear relation on B can be written as alpha 1 U1 plus da 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 plus alpha k UK plus beta 1 V1 plus da 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 beta m Vm is equal to the 0 vector. Okay? And this 0 vector, I think I have to specify. This is V, W. Okay. So T is equal to VW. Okay, and this is 0 vector in the vector space V. Okay, so we consider a linear relation on B. This is arbitrary linear relation. All right, so now we're applying the linear transformation T on both sides. We have alpha 1 T U1 plus da 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 plus alpha k T UK plus beta 1 T V1 plus da 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 plus beta m T Vm equal to T of 0V. But the 0 vector has image 0 vector in W here. And also, because U1, U2, UK, they are in the kernel of T, so that the image is 0W. This is 0W. Okay, so they are all zeros. So that okay, so we have, and this is W1, this is Wm. Okay, so we have, so now beta 1, W1 plus da da da, beta m, Wm is equal to 0 vector. But as we know, W is the basis of the, so the W vectors, so this set is linearly independent. So this implies that beta 1 equal to beta m equal to 0. Things. It's a linearly independent set. Right? Okay, so now we have shown that in this linear relation, the beta coefficients are all zeros. So that we have alpha 1, u1 plus plus alpha k, uk equal to 0v. But this also implies alpha 1 are all zeros since u1 up to uk is a linearly independent set. Okay, so all the coefficients are zeros now. So if we have a linear relation, we find all the coefficients are zeros. So that B is a linearly independent set. Okay, so we prove that B span V and B is a linear independent set. So V is a basis for V. And so the size of B, so the dimension of V is equal to the size of V, and the size of V is K plus M. But K is the dimension of the kernel of T, and the M is the dimension of the range of T, and we have done the equation. So now we have the conservation law already. Now an application of the theorem we just proved to an arbitrary matrix give us the following rank nullity theorem. Okay, the name is called rank nullity theorem for an M times N matrix A. We have the rank of A, okay, plus the nullity of A is equal to N. I will explain what is the nullity of A later. Okay, so in chapter 2, theorem 2.3.1, the matrix A defined a unique linear transformation T from Rn to Rn over from Cn to Cn. Okay? By T V equal to AV. Okay, for all V in Rn or in Cn. Okay, so a matrix A define a linear transformation. Okay, here. Oh, sorry, M. Because the matrix M times N. Okay, I'm sorry, please correct it. M. Okay, so now the kernel of T is equal to the kernel of A. Okay, and it's also called the normal space of A. Okay, in chapter 1, right, we know the kernel of A is just the set of all solutions of the homogeneous linear system, right, created by A, and it's also called the normal space of A. Okay. And also the range of the range of the linear transform is just equal to the column space of A. Okay. This is we know in chapter 2 already. Okay. So the kernel of T is the normal space of A. The range of T is equal to the column space of A. Okay. Now, by the previous theorem, so by theorem 5.2.17, we know the dimension of the kernel of T plus the dimension of the range or of the dimension is equal to the dimension of of the domain which is N. Okay, so this is the dimension of the normal space of A. Okay, because of the equality here. So this implies that, and the range is equal to column space of A. So this is dimension of the column space of A, and which is equal to N. Okay. Now, the dimension of the null space of A is called the nullity of A. Okay? So the dimension of the null space of A is called the nullity of A. Right? So this is by definition. And we know the dimension of the column space of A is just the rank of A, as we have shown before. All right, so finally, we have nullity of A plus the rank of A is equal to the N. And we have done. So basically, this theorem is an application of the previous theorem. Okay. Questions? Right, the last theorem in this section saying that the dimension of the row space of a matrix A is equal to the dimension of the column space of A. Right? So that is the statement of this theorem. Proof. Okay, so as we know, for example, For example, here, because every row, every non-zero row has a pivot as the leading non-zero entries. So that every non-zero row, okay, has a pivot. And below or above the pivot, the entries are all zeros. Okay? So apparently, so it is clear all right, so U is the reduced low echelon form of A. So it is clear that the set of all non-zero rows of U, okay, is a basis for the row space of U. Clearly, because the row space is spanned by the non-zero rows, and the set of all non-zero rows are linearly independent. All right, so it's clear. U is that. Okay, so that the dimension of the row space of U is equal to the number of pivots in U and equal to the rank of A. Okay, so this is from the observation of the reduced low echelon form of a matrix A. Because U is so simple that to see the result here. Since A is row equivalent to U, the row space of A is equal to the row space of U. Okay? So we know these two row spaces are equal by theorem 5.1.9. Okay? So that dimension of the row space of A is equal to the dimension of the row space of U, and this is equal to the rank of A, but the rank of A is equal to the dimension of the column space of A. We proved that already, so here is the result. And we finish the proof. Okay? All right, and so we know that this is equal to rank of A. And so this is called the column rank, right, of A. And this one is called the row rank of A. So another statement for theorem 5.2.19 is that for a matrix A, its row rank is equal to the column rank and is equal to the rank of A. So the three different concept of rank of A, column rank of A, row rank of A, these three numbers is indeed the same number. Okay? Questions? Okay, no questions. So I stop here and take a break. And we will start the quiz at 11:20.